Hello everybody, my name is Marie and I'm here with Engineering Outreach once again to give a little activity and learn a little bit more about STEM. What's STEM? Science, technology, engineering, and math. And today we're going to be talking a little bit more about a job that's relevant to our software engineers. So, what are software engineers? Software engineers do a bunch of different things, but they're focused around the design of new softwares or existing softwares. So they'll be doing a whole bunch of coding, either developing new code for applications or general softwares, websites, that type of thing, or creating reusable code that can be used by other companies or other networks to create other softwares. So that'll be mostly the job of a software engineer. They'll be working with coding, computers, websites, apps, and even at times video games. So today we're going to be talking about what shaders are. So shaders are used, originally were used to kind of give depth to a 2D space to make it seem more 3D. So it sort of applies kind of a general feeling of light or shadows. So it kind of gives the illusion or simulation of light and shadows that we have in our real world into a 2D screen to make our environment look 3D. So it uses a bunch of different types of languages. All of them are usually C-based because we'll be using like a C++ programming language that kind of ends up with more layers or changes a little bit that's specific to shaders. So when we're talking about shaders, we have different languages like high-level shading language, HLSL, or for example, OpenGL shading language, GLSL. And that's the one that we're going to be talking about a little bit more today. So, in general, where would you have seen shaders in usual life? Well, the most talked about applications is definitely video games. So if you think about Minecraft, that's a really easy place to start because if you've played Minecraft before, you know that it's possible to get custom shaders to kind of make your game more realistic or more real looking. Because Minecraft at its base is not a super realistic looking game, but it can look really nice if you add in different types of shaders that you can even make yourself. So as I said earlier, shaders are used in games or websites or softwares, that type of thing, to give a more 3D effect to the 2D world on the screen. So there's different types of shaders, and usually if we're using our own custom shaders, it'll go through these 3 different types in order to have a nice finished product. So we can talk about vertex, geometry, and fragment shaders. So starting off with vertex, it's the very first shader that's going to be used, and it's kind of used to break down 3D objects into a type of mesh. So if you have, for example, on your screen an elephant, it's going to break down your elephant into recognizable sort of geometrical patterns. So it'll be easier to calculate where there's supposed to be shade or light, etc. And so once our 3D object has been like deformed into different geometrical meshes, we're going to move on to the vertex shaders. These vertex shaders are going to come in and actually do some extra work and get these geometrical shapes and look at where their vertexes are. So they're vertices or vertexes, and they're going to do some extra work to understand where those should be and where the shade should be off of that. And then our last shader, which is our fragment shaders, and these will actually just come and calculate whether the presence of the shading pixel is necessary at that spot or not. So it's really just kind of like our final one that makes the decision, should it be shown or not. So essentially, just to kind of go over the process again, you can kind of imagine if you have your 3D object, the first step is breaking it down into a mesh. So kind of breaking it down into a bunch of small pieces so it's more easily recognizable geometrically. And then once we've broken it down into these geometrical shapes, we move on to breaking it down into vertices. So these vertexes, and then we have a bunch of operations that are done to determine their position, like relatively to other things or to light sources, that type of thing. And then that information, so the information is gathered from the first step, from the second step, and then is passed on to the fragment shaders, which use it to fill in the space accordingly. So yeah, today we're going to be using a shader development tool called ShaderToy. So if you've used a game development software before, such as Unity or Unreal, you'll have definitely had experience in adding shaders into your environment, but usually it's done sort of automatically. In the case of Unreal or Unity, the shaders are actually already like built into the system somehow. So they use like an abstraction on top of HLSL, so that's one of our shading languages, called ShaderLab. That'll kind of handle all those calculations, all that coding for you. ShaderToy, on the other hand, is a software that allows users to create pixel shaders. So essentially, we're jumping right to fragment shaders. We can just kind of like draw every pixel on the screen type of thing. So we use to code in ShaderToy, as I said earlier, GLSL, I believe, yeah. But what we code will actually be shown using JavaScript, HTML, and CSS. But our coding will be done in GLSL. So ShaderToy does not have access to vertex shaders like Unity or Unreal does. So not as many optimizations can be done or are done for you. So it means you have to really rely on your algorithm and what you want to create with your code. So ShaderToy is a great way to practice if you guys want to create your own shaders and kind of help you think more algorithm-wise, more mathematically into what you would want to accomplish. So I'll switch over to my other screen and we'll take a quick look at the website. So this is what ShaderToy looks like. And as we can see some community work already that's been done on ShaderToy. So for example, we've got this one here, and just different ones that are just kind of cool. We can see the type of work that people have put into this, and all this, again, using just like an algorithm, just some code, so it's really quite impressive. So, moving on to what we want to look at specifically, in order to kind of discover what we're going to discover today, we can go right into New. If you want to sign in, you can sign in, create an account and such, but if you don't want to, you can absolutely just press New and you will have the screen ready for you. You'll be able to edit the code however you like. So when we come in here, we've got about 4 lines of code, and looks pretty simple, but you take a closer look and it looks pretty complicated. So we've got these different inputs here. So our very first line of code here, if you guys are familiar with coding, then this is going to be clear for you. This is really our entry points. So this is really where our code is going to be starting. This is our main loop, and this is our entry point once again. So this is just going to be the very beginning of our code. Then we can move on to the second line here. So the second line looks a little bit complicated, but essentially when we're working with shaders in this language, we'll be using primarily what we call vectors, or the VECs that you see on the screen. So we can see on the screen, this one is VEC2. So vectors, if you've seen it in school, vectors are usually in different dimensions. So if you're still in high school, usually you'll only have seen vectors in 2 dimensions, or maybe even 3. And in university, you'll definitely know a little bit more about that. So we can kind of keep that in mind. So our vector 2 here will be a 2D vector. So this is going to be kind of initializing for us this screen that we have over here. So it'll be kind of normalizing the pixel coordinates from 0 to 1. So if we come down into the corner over here, this is going to be our 0, 0, this is going to be 1, 1, and so down here we could have 0, 1, and then 1, 0, or 1, 0, 0, 1, my bad. Yeah, so this first line is just going to be us making sure that our screen here is calibrated to indicate that this is our 0, 0, and our 1, 1 over here to make sure that we stay between 0 and 1. In order to stay between 0 and 1, that's how we're going to use this division here, frag core divided by iResolution.xy. This is just going to make sure that our values, again, stay between 0 and 1. It makes our coding a lot simpler afterwards. Now, our second line, we can see we've got vec3. So this is what we would kind of see as like a 3D vector. But this time, it's a vector that would hold 3 different values or coordinates. And in our case, since we're not working with the actual space, we're working with colors or lights and such, this is actually going to hold 3 different values like RGB, red, blue, green. So here, our definition for this vector is quite complicated. There's a lot of math here, and this is just the math that's going to make it possible for it to be changing colors like this and changing hues. So the math here looks pretty complicated, looks pretty scary, but it's really just making sure that we can see what's on the screen here and the way that it's changing. And then here, our very last line is as written, the output to our screen. So this time we've got a 4-dimensional vector, and this one is going to have our RGB as well as a 4th dimension that's going to be dimensioned very lightly. It's not really a dimension, but it's just kind of our 4th value in our vector, and that's going to be the opacity. So opacity could range between 0 and 1, and here we've got 1 here that makes it completely opaque. So yeah, those are pretty much the 4 lines that we have now. If we wanted to play around with it, we could just go ahead and change something basic. So we could look at this second line inside of the void main image that we have. And this math is quite complicated, so let's kind of change it around to something a little bit easier. And instead of this complicated math, I'm going to change it over to vec3 uv 0. So this is essentially going to make it so that we have our RGB is going to be defined for R, for G, but not for blue. Our blue is always going to be at 0. So if we were to press play, we'll see we've got no blue. To make it a little bit clearer, what I can do is write X here, Y. Oh, sorry. That is meant to be a, oh, wow. There we go. So now that I have it on the screen, it's a little bit easier to explain. So UV is going to be kind of any point that's anywhere on this screen. So if we're starting from here, it could be this point here, this point here, this point here. It could be any point. So the vector UV is any point on, so if we're following, for example, UVX, so we'd be down here, this is going to be our R, so our red. So we're going to start from 0 and go till 1, right? So we're going to go 0.1, 0.2, all the way until 1. So when our UVX, so when our red is at 0, obviously we'll see some black. And then as we progress all the way along this line, we're going to make it all the way to 1, and then we're going to have our full red. Similarly, if we look at UVY, this one, this time, is going to be our G, our green. So if we start at 0, we're just going to have black. And we're going to go all the way up until we make it to 1, and then now our green is going to be a full green. Now, if we're kind of thinking about points that are out here in the space, like this point here, kind of orangey, that means we are making it all the way down here on the x-axis, so we're at maybe 75% of the red, and then we're making it all the way up here on our y, which is maybe at a 60% of our green, and when they meet in the middle here, they kind of mix together and they make this orange color. And then again, if we make it over to 1, 1, we see the mix between the red value, the absolute red value, and the absolute green value make a yellow. So if we were, for example, to come over here and change this 0 to a 1, now we have a blue, and it changes everything entirely. It's a little bit harder now to understand exactly how it works, but it's essentially the same thing. So now we'll have a blue that's spread out all over our canvas, and our X and our Y is going to change again accordingly. So if we've got our blue, but our X axis is still our red, as we progress we get more and more red until we finally make it to pink. Over on the Y axis we get more and more green until we make it to cyan. And then on both ends, as we have all the colors together, we'll finally get some white in the corner on the right. So using these different inputs, we're capable of creating pretty much any color we want with a really, really high precision. So we can mix different colors, find different things, kind of use our color theory to understand exactly what's happening and what's going on. Now this is a really basic code with ShaderToy, but we can do a lot more complicated things. If we go over into the Browse tab, we can actually see things that have been done by users. And these can get really, really cool. So for example, if we look over at this one, this is what they managed to create using Shader Tool and GLSL. So here we've got their very long code that kind of explains how they made this. So obviously, this code is a lot more complicated than what we just saw, but as we see on the screen, it does yield really nice results. So ShaderToy is really something that's very fun to play around with. GLSL can become kind of a complicated programming language to use, and it's very specific to shaders. However, it'll make a very high precision and cool effect if used properly. So that's pretty much all we had going for today. Just kind of the basics of starting to discover what shaders can actually do and what we can learn from them. Again, making customizable shaders is a really cool activity and can add a lot of depth to your experience. If you're into gaming development, or even just want to add on to games or mod whatever aspect of a game that you're playing, shaders is always an interesting thing to approach and look into. So thank you for